So 9.7 is going to kind of serve as a mid-chapter kind of review of basically 9.2 to 9.6. 9.7 is basically, as the title suggests, a bunch of strategies for testing series. Since we started 9.2, which is really the proper start to chapter 9, we have a bunch of tests for figuring out if series converge or diverge. So we need a kind of way to kind of manage all that so that we have a good plan when we see an infinite series and we're trying to figure out if it converges or diverges. You can kind of relate this back to when we first started integrating. And then once we started collecting more and more ways of integrating, you needed to be able to look at an integral and figure out, using some sort of methodology, which kind of an integral you were trying to do. Kind of the same thing applies here. We're going to have a random infinite series given to us, and we need to figure out whether it converges or diverges, so we need to figure out what test would be appropriate to use to figure that out. So unfortunately, there really are no rules about which test to apply so that this always works. There are flow charts and things of that nature that kind of tell you what to do, but really the best way to do these problems is just to A, get practice, of course, but B, understand the kind of form you're looking for to use the different kinds of tests we have. So I don't think it would be smart just to go down the list of tests and just kind of use them until something works. That would certainly waste a lot of time and effort. So the main strategy we're going to use is to classify the series according to its form, which again is kind of how we did things back when we were first integrating. Once we collected a bunch of different ways to integrate, you needed some sort of way of figuring out what your strategy was. And kind of the way we did that is we kind of needed to see what was going on and then of course approach it accordingly. So that's what this section is dedicated to. There are no more tests here, or I should say there are no more new tests. We're just going to try to figure out the best way to manage all of these tests so that we can test infinite series. And kind of like you saw me doing a lot of the examples I did, the first thing I would do is use the nth term test, because it's a quick one, and if it works, you're kind of done with the problem. Of course, unfortunately, a lot of the times it won't work, but certainly when it does, you should use it. And the nth term test just quickly stated that if you take the limit of your infinite series and don't get a 0, then that series diverges. So just as a quick example of that, if we were to take the limit of this infinite series, we'd get 1/3, which would say we could just come to the conclusion, I should say, that it diverges by the nth term test. We didn't have to do a comparison test or any of those other involved tests. The next thing we saw, and I'm going to kind of go in order of the way we saw these tests in terms of the strategies here. The next thing we saw was a geometric series, and it had one of these two forms. If you ever see anything that looks even remotely close to that, or if you can do some algebra to get your problem to look like this, then you know you're going to be using a geometric series kind of idea. And again, as a review, if that r value is less than 1, the geometric series converged, and if it was bigger or equal to 1, it diverged. So yes, please note, if you remember a lot of the problems we did, there usually was some algebra we needed to do before this could look like a geometric series. And if you remember, it usually was something along the lines of like 1 over 5 to the n, which was then rewritten as 1 to the n over 5 to the n, or 1/5 all to the n power. That's really the algebra that I was talking about, but you never know what kind of problem you might see. In this particular example, we don't have to rewrite it, it's already written as a geometric series, so we can kind of take what we know. Pi over 6 would be roughly what? Well, if pi is 3 roughly divided by 6, that's certainly going to be less than 1. So then because of that, we have a geometric series where r is less than 1, or we can come to the conclusion that that series converges because we know about geometric series. Okay, continuing on with these strategies, one of the very basic and luckily most often used is a p-series kind of a test. If you ever see a series of this form, or you can get a series to look like something of this form, then we know that it's a p-series, and if p is bigger than 1, the series converges, and if p is less than or equal to 1, the series diverges. After that, if we don't have a p-series or a geometric series and our quick test, the nth term test doesn't work, we have to jump into all of those tests that we saw in these previous lessons. So here's the good news about the direct or limit comparison test, depending on which one you like, if you have the choice of which one to use. If you have an infinite series that looks like a p-series or a geometric series, the best thing to do usually is to do one of these comparison tests. In particular, rational functions where you have polynomials should be used or should be applied for this direct or limit comparison test because they are basically p-series. And of course, when you're dealing with these comparison tests, you're trying to find the essence, if you kind of remember that idea back from 9.4. So anytime you see something of that form, probably a direct or limit comparison will be appropriate, and that would kind of be in this case here. 1 over 3n plus 1 looks a lot like the harmonic series if you wanted to compare it to that. And I'm not going to kind of do the problem here, I just kind of want to go over these strategies here. But if you did do this problem using a limit comparison test, you would find that this infinite series diverges once you do that. Another strategy, and it's probably one of the easiest to identify, is when we have an alternating series. Anytime you see something with infinite series that has that or that, we know that that's an alternating component, so it's an alternating series, and it's probably the most obvious problem you're going to do. If you recall, there's 3 checks you have to do to make sure the alternating series converges or diverges, and 3 checks you have to do is the general term positive? Yes or no? That would be a check. Are the terms decreasing? Yes or no? That would be a check. And does the limit equal 0? That would be the 3rd check. And again, you're doing that to the non-alternating part. So we would be doing that just to the 3 over 4n plus 1. We ignore the alternating part. Again, I'm not going to do each of those steps here for this problem, but if you wanted to write all of this out for this particular problem, we would say that this series converges by the alternating series test. Last section we studied the ratio test, and you hopefully made a note that anytime you see factorials or other products, including constants raised to an nth power, kind of basically what I'm getting at here is the really complicated looking ones, the ratio test is a fantastic one to use. Unfortunately though, the ratio test should not be used when something looks like a p-series. The main reason is because you'd end up with an answer of 1, and that's an inconclusive result. So in those cases, you really need to use a comparison test. But outside of that, we need to set up this ratio to do the ratio test anytime you're going to apply the ratio test. So certainly in a problem like this, it doesn't look like a p-series, it doesn't look like a geometric series, it's got a factorial in it. So this is a great candidate for using the ratio test. Again, I'm just going over these strategies here. So if you wanted to do this on the side or to try this on your own, if you applied the ratio test to this infinite series, we would find that the series diverges. Another test that may or may not be useful, but if you remember what I said in the last lesson, the root test really doesn't show up, I believe, on the AP test, but certainly if you saw an infinite series that was all raised to an nth power, then the root test would be great to use. The reason we couldn't use that in the one above is, of course, the top doesn't have a power of n. But if everything has a power of n, just like this example, then a great test to use, of course, would be the root test. Again, I'm not going to do this problem. I just kind of want to go over these strategies. But if you apply the root test here, you'll find that this series converges. Again, there really is no list you should be going through to apply apply these tests, but to be perfectly honest, the integral test should be a last resort. The integral test is probably the hardest one in a sense, because you have to go through this whole integral process of this improper integral, and that may or may not be easy in some problems. So while I don't want to imply that this should be the last test you consider, it really should be. Mainly, again, because you have to be able to integrate your infinite series. Whatever that infinite series is, you have to be able to integrate it in this improper integral. So in a problem like this, that would be a very useful thing to do. We can certainly integrate this function here. The integral of x e to the negative x squared could be easily evaluated. And again, I'm not going to go through that problem, but ultimately, by the integral test, that series would converge. And if you just need the extra little info here, if you were going to integrate this, of course, the u in this case would have to be negative x squared. And then, of course, you can do the whole process of the integral, but in this case, the u would be negative x squared. And by the integral test, we would see that this series converges. Okay, in these next couple slides here, we're just going to be given an infinite series, and we want to determine if that infinite series converges or diverges. So, of course, because of that, we need to know some sort of strategy for figuring out which test we're going to use on these infinite series. So what test would be appropriate for this first infinite series? We really can't compare this to anything. It doesn't look like a p-series or a geometric series. We're certainly not going to take the integral of something like this. So really our only option here, and I don't want to make it sound like every test is going to be a ratio test, but this one's certainly going to be a ratio test. So let's go through this process. We need to set up this fraction here, but I'm going to skip a step, mainly because of space here. When we set up the a sub n plus 1 term, of course we're going to plug in n plus 1 in parentheses wherever we see an n. So we'll have n plus 1 squared over e to the n plus 1. And then if you remember, basically in every problem that we did with the ratio test, since we're dividing by our original infinite series, basically that always led us to the step where we need to multiply by the reciprocal. So again, for the sake of kind of keeping this a nice short process, I'm going to go ahead and skip that step and just multiply by the reciprocal, which would be e to the n over n squared. Okay, so what do we need to do here? Well, the absolute value, luckily we don't need, and in the bottom we can split that power. We can make the power we can split the power, into the product of e to the n times e to the 1. And the good news about that is we can of course cancel the e to the n in the top and the bottom, and then we're just left with this fraction, n plus 1 all squared over e times n squared. And then we just need to take the limit of that. In the top, of course, if we FOILed it out, we would have an n squared as the biggest term, and then that n squared would cancel with the n squared in the bottom, and when we take that limit, it's nice and simple. We just have 1 over e. Again, using the ratio test, we want to look at the result and see if it's bigger or smaller than 1. If it's less than 1, like we have in this case, then we know our infinite series converges, and in this case, by the ratio test. In this next example, it's kind of a leftover sort of example, and just for the sake of time and not spending too much time on a test we're really never going to see, if at all. This one's going to be a root test, and if you kind of want to go through these steps, I think it's a worthwhile problem to kind of see. But again, for the sake of time, and this not being too important of an example, I'm going to go ahead and skip over this explanation and go to a more appropriate kind of problem, and this one right here. As soon as you see a factorial, I hope you realize that the ratio test is kind of the way to go. And once we realize that, again, I'm going to kind of skip the step of setting this fraction up with a fraction inside of a fraction. There's nothing wrong with writing that out, but you know, if you are getting good enough at using the ratio test, we can certainly skip that step, but just realize we need to take n plus 1 and plug it in for n, so we'll have 2 to the n plus 1 all over n plus 1 factorial, and then we can just save some time here and multiply by the reciprocal of the original infinite series. Instead of dividing by that fraction, again, we can just save some space and time and just multiply by the reciprocal of that. But again, if you need to show that step like you would have saw back in 9.6, please do. Okay, so there's two things we can simplify. We can take the power of 2 to the n plus 1 and split it. 2 to the n times 2 to the 1. We can also take the denominator of n plus 1 factorial and simplify that. And luckily, we only need to expand it once because we get n factorial right away, which will of course cancel with that n factorial in the top. And then we have a 2 to the n power that will also cancel. The absolute value isn't necessary since we don't have any negative or alternating components, so we're just taking the limit of 2 over n plus 1, and of course that limit is nice and simple, it's 0. By the ratio test, as long as we get an answer that's less than 1, we can say that our infinite series converges by the ratio test. What about this problem? Well, in this particular case, the ratio test wouldn't be so good to use. The main reason is we don't have n powers or n factorials or stuff that's really making this complicated. You'll notice if we kind of take the essence of what we see here, it might be a comparison test. And again, if you're not told, you are free to use either the direct or limit comparison. So for the sake of me assuming this, I guess, I'm going to assume a lot of you would rather use the limit comparison. So if we're going to use the limit comparison, we need to compare this to something. And we're going to compare it to a p-series. If you want to jot this in, just realize in the top, really all that matters is n squared. In the bottom, all that really matters is n cubed. And of course, if we simplify that, that's just really 1 over n. So we're going to compare this series to the harmonic series 1 over n. But again, I'm just kind of going over some of these strategies. I'm not necessarily going to do these problems in their entirety. So we're going to compare it to the p-series 1 over n. And again, that's just our harmonic series, which diverges. In this next example, I hope these are again the obvious ones in a sense. We see an alternating component here. So by virtue of that, that must be an alternating series test. Again, I really wanted to go through the ratio test ones in their entirety, mainly because of the importance of the ratio test since we'll be using it the rest of this chapter. But for these last two that I did, if you want to try them and make sure you can practice the limit comparison and the alternating series test, that might be a good idea. Okay, in this last slide, just some more examples of trying to determine if an infinite series converges or diverges. And in this problem, realistically, it's not a difficult one to see. It's just kind of a big mess, which I think makes it difficult to see. Again, ratio test is probably not a good idea here because we don't have factorials or nth powers and stuff like that. Realistically, if we kind of simplify this, we can maybe find that it resembles a certain p-series. So that's what we're going to do. Again, we're kind of free to use either the limit or direct comparison if we're going to do a comparison. So again, I'm going to assume for most people, you'd rather use a limit comparison. So we're going to compare this series with a p-series. But what p-series does this infinite series have the spirit of, or the essence of? Well, again, we need to kind of consider the things that matter out to infinity. In the top of this fraction, the plus 1 doesn't really matter under the square root. And of course, in the bottom, the biggest power is really all that matters. And multiplying by 3 really doesn't do much of anything to infinity. So really the essence of this infinite series over here is the square root of n cubed over n cubed. So we definitely need to try to simplify that to figure out what p-series this resembles. So that square root with the 3 in the inside of it as a power can of course be rewritten as n to the 3/2 over n cubed. And when we have two bases that are the same being divided, we take their powers and subtract them. When you subtract 3/2 from 3, and I kind of had to skip that step, but you should be getting n equals negative 3/2 here. When you subtract 3/2 from 3, you'll get n to the negative 3/2, or sending that back to the bottom of our fraction, we'll get 1 over n to the 3/2. Of course, that's a p-series where p is bigger than 1, and then of course we can go through that limit comparison. In this particular problem, I've kind of been neglecting to say this through the problems we've been looking at, but again, we're kind of trying to identify the form. So I didn't really want to talk about that nth term test, the quick test, so to speak, until a problem like this. I guess we could maybe approach it as a comparison test, but that would, essence kind of be a waste because it really wouldn't work out, since the nth term test here will do the job just fine. You'll notice we can take this limit real quick, and it will give us something that's not 0. If we take this limit, we'll get 1/2, which is not 0, which means this infinite series diverges. So that's the good news. Anytime the nth term test can be used, definitely use it, and don't always resort to a harder method than is necessary. In a problem like this, again, we're not going to do the whole process of the problem, but you may or may not want to practice it if you have time. We see an alternating piece to this infinite series, so of course, that's just an alternating series test. In this next example, we've actually seen this problem, I believe, before, or one very similar to it in our notes. And when we did this problem from before, we needed a comparison test. The reason I know it's a comparison test is if we kind of ignore this 2, because we're going out to infinity, this looks a lot like a geometric series. And because of that, of course, a comparison test would be appropriate. Here, I'm going to write it out as a direct comparison. I suppose you could do it as a limit comparison if you wanted to. But just to be maybe more thorough in a sense here, I'm going to write that we could also use a direct comparison. And we're going to compare this unknown infinite series to the geometric series 1/3 to the n power. Again, we can rewrite 1 as 1 to the n, which would be over 3 to the n, which then we can write as 1/3 all to the n power. So hopefully that little algebra trick is still fresh in your mind. In this particular problem, it's very simple in a sense. It's only the infinite series of sine n. And we really haven't seen trigonometry much in these infinite series. Because of that, I guess the test that we might want to use here might not be obvious, but maybe let's just start with the test that we should maybe always start with in a sense if you don't recognize what to do, and that would be the nth term test, because as it turns out, if we take the limit as n goes to infinity of sine n, that doesn't exist. And remember, as long as we don't get 0, then this nth term test says that this series diverges. So that's the good news here. It was actually just a quick application of the nth term test. In this last problem, again, it may or may not be obvious when you're looking at these, so I always say, as a last resort, save the integral test for the ones that need the integral test. And for a problem like this, if you run through the list of possibilities with these tests, really the only one that's going to help us here will be the integral test, which would mean we would have to take this improper integral and evaluate it. And the reason that this is going to work out is because we can definitely do a u substitution here. After making our u substitution, we'd end up with an integral like this. And I didn't really have the space to animate it in, but you might want to write that this integral really becomes e to the u times x to the negative 2 dx. The reason we're moving that x squared from the bottom to the top is if you realize that your u is 1 over x, if you do the whole u box thing with du, you'll actually get this u substitution to work out. So again, we're not going to go through all these tiny details of this process, but ultimately, if you want to practice this and try to get this result, you should find that the integral, or the answer to the integral you'll get, is e minus 1. Ultimately, how are you going to take that and interpret it as an answer? Well, just remember, if we take an integral of this infinite series here and get some number, any number, e minus 1 is a number, it's 2.7 minus 1, then we know that that infinite series converges. And that's, of course, the conclusion that we're going to draw here. Since the result of the integral is e minus 1, we know that this infinite series over here converges. So to kind of summarize all of this, again, what we're really trying to do here is just come up with some strategies for applying these tests. Ultimately, it just takes the practice of seeing these tests being used that will really get you familiar with which test to use in whatever situation happens to present itself to you.